In this lesson, we are going to learn about probably the most complicated thing in all of Chapter 8, which is inverses of square matrices. Now, the first thing I want to talk about is this word right here. When somebody's talking about a matrix being square, what that really means is that you're going to have the same number of rows as you have columns. So if you have 2 rows, you're going to have 2 columns. If you're going to have 3 rows, you're going to have 3 columns. Remember, the rows go first, and rows are horizontal. Columns go second, and they are vertical. So the first thing that I want everybody to understand is, why do we even need this? It's going to be complicated. You're not going to like it. It's difficult. So there better be a really good reason why we need this. And there is. In matrix math, if you go back and take a look at the operations that we've done, we've learned how to add, we've learned how to subtract, we've learned how to do scalar multiplication and matrix multiplication. The one thing that you'll find is missing in all of that, there is no matrix division. So if you wanted to solve a problem like this, matrix A times matrix X equals matrix B, and you knew the value of matrix A and you knew the value of matrix B, and the one thing you didn't know was matrix X. What you normally do under these circumstances, if this was a regular equation, is you divide both sides by A. But that particular operation, dividing both sides by A, does not exist since there is no matrix division. So what we're going to do instead is we're going to multiply both sides of the equation on the left and on the right by the inverse of matrix A. So since there's no division, you can multiply both sides of the equation by the inverse of matrix A. What they use to represent the inverse is that letter, matrix, with a -1, what looks like a -1 exponent. So when I wrote A to the -1, that really means the inverse of matrix A. And whatever you're doing on the left-hand side of the equation, you have to match that by doing exactly the right-hand side, same thing on the right-hand side of the equation. So you can see I'm multiplying the inverse of matrix A on both sides. So the inverse of matrix A, when you multiply it with A, has the effect of canceling out. That leaves you with just X alone on the left-hand side, and on the right-hand side, you have the inverse of matrix A times matrix B. And we could just do our matrix multiplication thing to figure this out. As long as matrix A and matrix B, the inverse of matrix A and matrix B have that property that you can multiply them. The number of columns from the inverse of matrix A would have to match the number of rows from matrix B. Now, in order to go any further with the idea of inverses, I have to introduce you to another idea, which is an identity matrix. An identity matrix is a square matrix, again, square meaning the same number of rows and columns. So an identity is a square matrix with a main diagonal of 1s and 0s everywhere else. It looks exactly like what you get at the end of the reduced row echelon form. So that Gauss-Jordan process that we learned yesterday, the end product produced a diagonal of 1s and triangles of 0s below and above the main diagonal. That's what an identity matrix is. So here I'm going to show you a couple of identity matrices. So first of all, the one that's on the left is a 2 by 2 identity matrix because it has 2 rows and 2 columns. And the one that's on the right is a 3 by 3 identity matrix since it has 3 rows and 3 columns. Notice that the main diagonal is 1s and we have 0s everywhere else above and below the main diagonal. In the 3 by 3, there are 3 1s on the main diagonal and a triangle of 3 0s below and a triangle of 3 0s above. So 3 1s and 6 0s. When you name an identity matrix, you use the capital letter I, and then you put a subscript on it that says how big the matrix is. So I2 refers to an identity matrix that's 2 rows and 2 columns, and I3 is going to represent an identity matrix that has 3 rows and 3 columns. The reason why they don't put the subscript here twice is it has to be a square matrix, which means the number of rows and columns has to match. So when I say I2, we know that both the rows and columns have to be 2, or I3 means that both the rows and columns have to be 3. In general, there are going to be two main tasks that you're going to be asked to do with these inverse things. The first one is to prove whether or not two matrices are inverses. This is the easier of the two things that I'm going to ask you to do with inverses. Let's take a look at what this involves. To prove that two matrices are inverses, you have to multiply the two matrices together and show that the product is an identity. You must do this both ways since matrix multiplication is not commutative. So remember, the commutative property guarantees that you get the same answer either way. Matrix multiplication was not commutative, so we have no guarantee that if it works one way that it'll work the other way, so that's why we have to do it both ways. Let me show you what this looks like. And today we're going to focus only on 2 by 2 matrices, so we'll make it easy. Let's say I give you matrix A having the values of -1, 2, -1, 1, and matrix B having the values of +1, -2, +1, -1. And I ask you to prove whether or not matrix A and B are inverses of each other. So here's what you're going to need to do. Take matrix A and B and line them up and do a matrix multiplication. So remember, in matrix multiplication, whatever matrix is first, we're traveling across its rows, and whatever matrix is second, we're traveling vertically down its columns. Now, matrix A has 2 rows and 2 columns, and matrix B also has 2 rows and 2 columns. So the number of columns from my first matrix and the number of rows from my second matrix match. I will be able to do this multiplication. So let's actually carry it out and see what happens. In the top row, combined with the left column from matrix B, we're going to get -1 times +1, which is -1. And then second element times second element is going to be 2 times 1, which is 2. 2 and the -1 makes 1. That's going to go in the top left. Bottom row with left column is going to produce first times first, which is -1, and second times second, which is +1. -1 and +1 makes 0. So that's going to go in the bottom left. Top row with right column is going to produce +2 and then -2. So that's going to make 0 right here. And then bottom row with the right column is going to make -1 times -2, which is +2, and 1 times -1, which is -1. So we've got +2 and -1, which makes 1. So what I'm looking at right here has a diagonal of 1s and 0s everywhere else above and below the diagonals. So this is actually the identity matrix I2. Because A times B produced an identity matrix, I am halfway to proving that these two matrices are inverses of each other. If they're inverses, you're supposed to get an identity matrix, which we did, but you have to do it both ways. So the other half of this is now I have to take matrix B and matrix A, reverse the order, putting B first and A second, and repeat the multiplication. So now I'm traveling across the rows of matrix B, and I'll be traveling vertically down the columns of matrix A, because B came first this time and A came second. And when I multiply first times first, I get -1, second times second, I get +2, +2 and -1 makes 1. Bottom left is going to be -1 and +1, which makes 0. Top right is going to be +2 and -2, which makes 0. And bottom right is going to be +2 and -1, which makes 1. So again, you're getting a diagonal of 1s and 0s everywhere else. If you produce an identity matrix both ways, when you're multiplying A times B and B times A, then you can say for certain that matrix A and matrix B are inverses of each other. This is the easier of the two things that you're going to have to do in tonight's homework, proving two matrices are inverses. Multiply them together, show me you get an identity matrix both ways. If you only do it one way, you're only halfway done. So the second and frankly more challenging thing that you're going to be asked to do with inverses is if they give you just one matrix, they might ask you to find what that one matrix inverse might be. So instead of giving you two matrices and just checking to see if they're inverses, they might just give you one matrix and ask you to find what its inverse would look like. So a couple quick things on this. Number one, only square matrices have inverses. So if somebody asked you to find the inverse of a matrix and its number of rows and columns do not match, don't even bother doing any work at all. You would just say that there is no inverse for this. There are even some square matrices that do not have inverses. We call those square matrices that do not have inverses, they're called singularities. Now, what would happen in a square matrix that does not have an inverse is one of the rows would turn into all zeros. Once that happens, there's no fixing that and there's no recovering from that. So at that point, you would just stop and say this matrix does not have an inverse. But before we get into what it looks like when it doesn't work, let's talk about what to do when it is working. So let's say you do have a square matrix and that it's not a singularity. What are we going to do? So the way that we find an inverse for a square matrix, number one, you check to make sure it's square. Check to make sure that the number of rows and the number of columns match. If that's true, move on to step two. If it's not true, say it doesn't have an inverse. So assuming that the rows and columns match, the next thing you're going to do is write matrix A with an equal-sized identity matrix right next to it with a dotted line separating the two of those matrices. We call this situation adjoined matrices. So the matrix you started with, you're going to attach an identity matrix of equal size next to it. Put a dotted line in between them. Now, you're going to perform that Gauss-Jordan process. We also sometimes refer to that as the RREF process, reduced row echelon form process. So you're going to use the Gauss-Jordan process. That's the one where you do the Gauss part, and then you go back up the other side in reverse order to get rid of things above the diagonal. And you're going to turn matrix A into what looks like an identity matrix. So by the time you're done, matrix A will have a diagonal of ones and zeros everywhere else. And whatever math you're doing to matrix A to make that happen, you're going to do that math all the way across the dotted line onto what used to be the identity matrix. As you're doing the math to turn matrix A into an identity, that same math will be turning the identity matrix that was attached into the inverse matrix. So by the time you're done, what's on the right-hand side of that dotted line will contain your inverse for matrix A. Now, the last thing that you can and probably should do is you could check your result by multiplying the matrix you started with, matrix A, with what you believe to be its inverse. And remember, both ways, whether you multiply matrix A with its inverse or the inverse of matrix A with A, you should be producing an identity matrix as the answer. That's the way to prove that you have inverses of each other. So let's say that somebody asked you to find the inverse of the following matrix and then gave you this. A is 1, 4, -1, -3. Well, the very first thing that you're going to need to do here is you're going to need to check the size of the matrix. So I've got 2 rows going across and I've got 2 columns going down. So the size of this matrix is 2 by 2. Remember, that's important because only square matrices have inverses. If it is square, which it is, we are going to take the right edge of this matrix. We're going to take that bar off of there. And instead, we're going to change that into a dotted line. And on the other side of this dotted line, I need you to attach an identity matrix. So remember, an identity matrix has a diagonal of ones and zeros everywhere else. That identity matrix has to be the same size as matrix A. So my identity matrix has to have 2 rows and 2 columns as well. So this is my starting matrix A on the left, and this is my identity matrix on the right. My goal is to use the Gauss-Jordan process to turn this left-hand side into looking like this. So we're going to do the Gauss-Jordan process to turn this side into 1, 0, 0, 1. And as you're doing that math, you're going to carry the math all the way across, even onto this side of the dotted line, and this side will be changing into your inverse. So let's get started. The first step in the Gauss-Jordan process is to make sure that the top left corner of your matrix is 1, and it is. So we don't have to do anything with that step. The next step of the process is to use your top row to help you eliminate whatever's sitting in this first spot. Our goal is to try to turn that into a 0. So the way that I'm going to accomplish that is by adding the top row with the bottom row. Now remember, my goal here is to change the bottom row. So at this point, I'm not doing anything to change the top row. So I'm just going to leave the top row the way it was. 1, 4, 1, 0. Okay, to change the bottom row, I'm going to add the top row with the bottom. 1 plus -1 makes 0. 4 plus -3 makes 1. 1 plus 1, because you got to do the math all the way across. 1 plus 0 is 1, and 0 plus 1 is 1. So I now have a new bottom row that says 0, 1, 1, 1. This right now is already in row echelon form. I've got my diagonal of 1s and my 0s underneath. So that's the end of the Gauss part of the process. Now we're going to start the Jordan part of the process. So remember, what Jordan was looking for us to do here was to use rows underneath to help us get rid of things that are above the diagonal of 1s. In other words, we're going to have to try to eliminate that 4 right there. If you add the bottom row with the top row right now the way it is, that's not going to eliminate, that'd make 5. So you're going to have to multiply the bottom row by -4 prior to adding with the top row so that these can eliminate. Remember though, when you're doing that, that's only something you're doing temporarily, so you're not trying to change the bottom row. We want our bottom row to stay 0, 1, 1, 1. But when I say I'm going to multiply the bottom by -4 and add with the top, it's in order to make a new top row. So -4 times 0 added with 1 makes 1. -4 times 1 is -4, add with that makes 0. -4 times 1 is -4, plus 1 makes -3. And last but not least, -4 times 1 is -4, add with 0 makes -4. Now, over here on the left-hand side, we can see that we have a diagonal of 1s and 0s everywhere else. We have managed now to turn our matrix A into an identity matrix. It took some work. We had to do that Gauss-Jordan process to make that happen. And as we were doing that work on the left-hand side, our identity matrix that used to be on the right-hand side has now turned into your inverse matrix. So the answer to this question is whatever ends up on the right-hand side of the dotted line. That is your inverse matrix. So you want to make sure that you break that out separately so that everybody can see that you know what the inverse matrix for this problem is. It's not the whole thing. It's not both of these matrices. It's not what's on the left-hand side. It's only the part that's on the right-hand side. So your inverse matrix for A is -3, -4, and the bottom row is 1, 1. And you get that from the right-hand side of this adjoint matrix situation. If you want to check this, you could take this matrix, what we believe to be the inverse of matrix A, and multiply it together with the original matrix A. And you should get an identity matrix, and that would be true both ways. If you multiply A first times the inverse of A, and also if you multiply the inverse of A times A. You are now ready to try the homework for tonight. Again, we're focusing in tonight's homework only on 2 by 2 matrices. So they should be about this length in terms of finishing them.